Hello, pre-calc students. This is going to be our next day of sketching, some more transformations on functions, and sketching functions in general with a topic called piecewise functions. Now, piecewise functions are something that you learn about for the first time in Algebra 1 and certainly do a little bit more with it in Algebra 2. But essentially, a piecewise function is just sketching different parts of a function over some restricted domains. So we're saying, you know what, let's only graph this function when x is less than or equal to 0. And let's graph this function x squared when x is greater than 0. You know, having a good sense as to what these two things look like individually, I think will be important for making an accurate sketch in the end. But if at any point we're unsure about what these look like, I'll tell you my approach for you will be just to make a table of values. That's all we're going to do to be able to graph this successfully. So to get started right away with number 1 here, we want to make sure that for the function negative 2x minus 2, so let's start with that part, that when I make a table of values, I'm picking values of x that are in fact less than or equal to 0. So maybe I'll backtrack to like negative 3 and pick some values of x that get close and stop at 0 here, okay? So when I plug in negative 3, and just be careful there, negative 2 times negative 3 is 6, and then minus 2 is 4. Negative 2 times negative 2 is 4, minus 2 is 2, and we'll find that those y values will decrease steadily by 2 because that's the slope of this line. So that kind of makes sense to me. Now at that last point, 0, negative 2, what I want you to indicate is when we go to graph this in a second, since x can be less than or equal to 0, we can fill in a solid closed point at 0, negative 2. Whereas hopefully you're seeing that we're going to change that discussion when we graph x squared for x values greater than 0. All right, so now let's make a table for the function x squared. So even though it says pick values of x that are greater than 0, I do want you to start at 0. And then we can quickly say, all right, let's choose 0, 1, 2, and 3. So 0 squared is 0, and then 1 squared is 1, and that's 4, and that's 9, and that's all good. Okay, but at that point, 0, 0, the initial point that I chose, since x can't be equal to 0 for this function, what we're going to see at the point 0, 0 is in fact an open circle. And I'll discuss why in just a moment, why we didn't just start our table at 1, 1. But let's go ahead and make a set of axes. Plot the points that we've got here and see what this graph looks like. Okay, so you don't have to use different colors. I mean, I kind of like the way it looks, so you can definitely see what these two pieces look like. But we've got negative 3, 1, 2, 3, 4, and then negative 2, 2, negative 1, 0. 0, negative 2 is the last point we could plot for that linear function. And we do see that it should be a closed circle. So the thing is, I could have gone to x equals negative 4 and found the y value of 6 and x equals negative 5 and so on. So as you sketch this graph to the left forever, please just indicate that, you know, this linear function would continue on to the left side forever and ever and head up towards infinity there. So don't just stop at negative 3, 4. I mean, that's the last point we chose just to get an idea as to what this function looks like. So we're only seeing this linear function when x is less than or equal to 0. All right, moving over to the quadratic function. We know what x squared looks like at this point, but you're only going to see, you know, half of the normal parabola, right? If x is just greater than 0. So starting at 0, 0, put an open circle right there at the origin. And then we've got 1, 1, and we've got 2, 4. And if you want to plot 3, 9, go for it, guys. But I don't think we really need it to know that that's what the pattern for y equals x squared would look like, but only when x is greater than 0. So just a quick note as to why you need to start at 0, and you can't just say, oh, well, the first integer bigger than 0 is 1. It's because there's a lot of numbers that are bigger than 0 in between 0 and 1. I mean, I could have plugged in 0.5. I could have plugged in 0.2. I could have plugged in 0.1. Could have plugged in 0.0001. Those numbers are all values that are bigger than 0. But just to kind of get an idea as to what's happening as I approach x equals 0, but at that coordinate, we just have to make sure that we're putting an open circle. Can't include that as part of the graph. So of course, what we'll see for piecewise functions is that they do have typically some discontinuities. So if I asked you, where is this graph discontinuous? Remember that the discussion for discontinuous is just a value of x, where we have a jump or a hole in the graph. So this graph is discontinuous at just x equals 0. That's where we have this jump right here. And mainly what you should be able to do is probably just even look back to the original function at where that split happens, at what value of x, and then probably just make a conclusion like, oh, well, if anywhere, that's where we'll see a discontinuity. If I asked you where the graph was continuous, that's a little bit of a different discussion, right? Continuous are intervals over which the graph is drawn. So that would actually go from -infinity up to 0. Okay, 0 is included when I go from left to right, right? Because there's a closed circle. But then once I jump up to the next part of the graph, then it's continuous from 0 to infinity, but 0 is not included for the parabola. Okay, so just to kind of show you and remind you what the difference of asking about discontinuous versus continuous looks like in this context. All right, let's go ahead and try another one. So for number 2, f of x is going to equal 2x when x is less than or equal to -1. And then we'll do the function x minus 1 when x is greater than -1. So the functions that I've chose here are both linear in nature. So I'm hoping that, just to get started here, these are functions that we're really familiar with what the graphs look like. And I really do think tables of values are nice to help us remember and get an accurate sketch here. But I want to make sure for the first one that I pick values of x that are less than or equal to -1. So maybe I'll do like -3, -2, -1. 2 times -3, this would be -6, -4, -2. And at that final point, -1, -2, we should see a closed circle. We can include -1 in the domain for this graph because it says x is less than or equal to -1. Then if I move on to the next function, x minus 1, same deal. Let's pick values of x that are greater than -1, like -1, 0, +1. So -1 minus 1 is -2, 0 minus 1 is -1, 1 minus 1 is 0. Okay, but go back to the first point of this interval and say, hey, really that should be open because x had to be greater than -1 here. All right, maybe you're questioning something. At least I hope you're questioning something as I'm drawing some axes over here. Maybe you're catching on to something that's unique about this example. But if I start graphing the first linear part, 2x, we get -3, -6, 2, well, maybe I'll even skip that one. -2, 1, 2, 3, 4, and -1, -2 is a closed circle there. Okay, so that first part of the graph is going to be this linear function y equals 2x, but I got to stop at x equals -1. So then what happens in the next part of the linear function is that it's going to pick up at -1, -2. What? Wait, we have a closed circle there already. So that's what I was kind of referencing a minute ago. Like, what happens when there's an open circle and a closed circle in the same space? What I'll tell you shouldn't do is kind of put an open circle around the closed circle. I mean, that's cute and all, but it just doesn't make sense, okay? So try not to think of it that way, but just know that the closed circle overrides the open circle. So this value is going to stay closed. So I can actually just pick up from -1, -2 and go 0, -1 and 1, 0. And, the slope of this line kind of gets broken, right? It went from a slope of 2 now over to a slope of 1. But because this graph picks up exactly where this one left off at the point -1, -2, we would actually find that this graph is not discontinuous anywhere. It's continuous over the set of all real numbers. So if I said, where's the graph discontinuous? The answer is nowhere. If I ask you where this graph is continuous, you would say actually over the set of reals from -infinity to infinity. We can draw the entire graph without picking up our pen or pencil. So even though I said at the beginning, piecewise do typically have these little jumps in the graph, here's clearly an example where that's not true. It doesn't have to have those jumps. All right, so as normal, I think now's a good time for maybe you to try one on your own. I'm gonna give you 3 pieces for this next one though. Okay, so if you're a little confused, you can certainly wait for me to go over it, but I would recommend giving this a shot and see how far you can get with -x minus 1, when x is less than or equal to -1. Then in the middle, I'm going to say f of x equals 3 when x is between -1 and +2. Notice how I'm saying x is just strictly greater than -1, but it's less than or equal to 2. And then finally, the radical function, x minus 2, with a +3 after it, when x is greater than 2. Okay, so with 3 pieces, all that really means to me is that we need 3 tables. So again, go ahead and try this. If you want to give it a shot, you need a table for -x minus 1. Okay, pick those values of x that are less than or equal to -1 and do the same thing for the others. I'm going to start filling in my answers though right here. All right, so when I plug in negative, let's go back to like -3. Negating -3 is +3, and then 3 minus 1 is 2. And what you'll see is that these y values will decrease by 1, because the slope of the line is -1. At that last point, do we have an open or closed circle? Since x is less than or equal to -1, we can fill that circle in. Okay, you're really going to like the table for f of x equals 3, because no matter what the value of x is, the y value should be 3. Now, the x values for this table are from -1. You might as well go all the way till 2, right? Kind of include a list of all of those points there, but the y value is constantly 3 for each of those. And think about what's happening at the 2 endpoints of this interval. When x is -1, we definitely need an open circle. But when x is equal to 2, we can have a closed circle at the point 2, 3. And then finally, for the last part of our graph here, for the square root of x minus 2 plus 3, we would need values like 2 and 3 and 4 and 5 and 6. I'll explain why I'm adding a few more values to the table here in just a second. All right, so if I plug in 2, we get 0 under the radical. Square root of 0 is 0, plus 3 is 3. If I plug in 3, you're going to get a 1 under the radical. Square root of 1 is 1, plus 3 is 4. If I plug in 4, I get radical 2 plus 3, which is all fine and great, but I don't really want to write decimals down, so I'm going to ignore that for now. Same thing with 5. I mean, 5 minus 2 is radical 3, which is about like 1.7-ish. But, you know, I only really like perfect squares underneath there for now. 6 works nicely, doesn't it? 6 minus 2 is 4. The square root of 4 is 2. And then plus 3 would be 5. So that's kind of a nice point to include. But remember that that first part should really, where x equals 2, should be an open circle. Okay. So if I come over and make a sketch of what's going on here. Okay, there's my axes. We've got -3, 2, and -2, -1, and -1, 0, and we stop there for a second with a closed circle. All right, go ahead and connect that line going to the left forever and ever. All right, then we jump up to the point -1, 3 in the next table. So 1, 2, 3, that's an open circle, and it's constantly equal to 3 until we get to that point 2, 3. So we get a constant function in the middle. And then finally, the last part of the graph is going to be this radical function, which we know what that looks like. And the starting point is at 2, 3. Now, even though it says open, oh wait, did we recognize that it's already closed from the last part of our graph? So therefore, we can actually keep it closed and just keep going. We've got 3, 4. And if I jump all the way to 6, 5, just that extra point there gives you one more accuracy point to complete the graph. So in this case, we had 2 potential places where we could have had discontinuities, right? We get split up at -1, we get split up at x equals 2. But in fact, the graph is only discontinuous at x equals -1. X equals 2, I can draw the graph without picking up my pen. But if I ask you, where is this graph discontinuous? It's discontinuous only at x equals -1. Only place we have that jump. Okay. Last part of today's lesson is a little bit more with piecewise, but it's a different skill for us. We'll work on this more in class tomorrow. It's rewriting an absolute value function as a piecewise function. So for example, if we start with what we know the parent function absolute value of x to look like. Okay. Absolute value of x looks like this. All right, we have that V shape. And the thing is that you can actually break up an absolute value function always into two different linear functions. I have one line on the right side of where that V happens, and then we have a different line going on the left side of that V. So where this absolute value hits its vertex, right down the middle here at x equals 0, we're going to split the graph up there, and we're going to say, hey, on the right side of 0, we have a line with a positive slope, but on the left side of 0, we have a line with a negative slope. So I'm going to translate this function into not even having absolute value anymore. I'm going to say, you know what, this is f of x equals the line, here's the line y equals x. And when am I seeing the line y equals x? When I'm to the right of 0. So then what am I seeing when I'm to the left of 0? When I'm to the left of 0, I'm seeing the line y equals negative x. When x is less than 0. Now, the question becomes, I think commonly, like, where do I put the equal to? Do I put it with the x? Do I put it with the negative x? And I'll tell you, it does not matter. Doesn't matter. As long as you put it in one of those two places, that will include the vertex at 0, 0. If you forget to include it, that's a little bit of a problem, because then you would have this graph right here with the bottom open circle, which we don't want. Okay. But as long as you include the equal to part in one of these intervals, you're good to go. And that's exactly what this graph looks like, right? I mean, if I started with this and I said, hey, sketch this, in the end, you would sketch something that looks identical to absolute value. So let's just try one more of these, because maybe it's something that I don't know where the vertex is. Maybe it's something like 2x minus 1. If you're not sure where that turning point occurs, right here I knew it was at x equals 0 because we know what that parent function looks like. But to find the vertex, what you can do is set what's inside the absolute value equal to 0. And by doing that, we're going to get 2x equals 1, and therefore x equals a half. So even though now I know that the turning point occurs at x equals a half, I want you to put x equals 1/2 on a number line. As this is a little bit more of an algebraic approach rather than looking at the graph of this. And I'll tell you, if you pick something to the right of 1/2, like x equals 1, and you plug it into this function, 2 times 1 minus 1 is positive 1, isn't it? So I'm going to write that it's positive on this side. If I pick something to the left of 1/2, like 0, I would get 0 minus 1, which is a negative number. How does this number line help me to break this up into a piecewise function? So where you see that we have a positive part on the number line, which is to the right of 1/2, you're going to leave this equation identically the same. So you're going to see the line y equals 2x minus 1 as long as x is greater than or equal to 1/2. Okay, that's where the split's going to happen. That's where that vertex is. And since whatever I plug in over here keeps this quantity positive, I can leave that equation the same. But since whatever I plug into the left of 1/2 would make this a negative quantity, when I drop those absolute value bars, I'm going to negate it and say we're going to get the line negative 2x plus 1, right? Negate both parts there, when x is less than 1/2. And that is a way to take this absolute value and write it as a piecewise. Just kind of real quick here to think about what this looks like. The turnaround point that I said is at 1/2. So if you think about splitting your graph up at x equals a half, to the right side, you're getting the line 2x minus 1. And to the left side of x equals a half, you're getting this line negative 2x plus 1. Okay. We will definitely do more of this in class because this can be a tougher concept sometimes for students, but hopefully you understand how to sketch piecewise from earlier in the lesson, and we'll do a quick recap tomorrow. Have a good day.